Hello again. This is, I believe, video number 5, maybe on chapter 4. So we are going to continue. I hope you're doing well. Let's get started. So we are going to talk about the next section, which was derivatives of and the shapes of graphs. Okay. So let's talk about that now. We learned that one interpretation of derivative is the slope of the tangent line at any given x value to the graph of the function. So the slope of the tangent line, for example, at this point is that, at this point is that, at this point is that, right? So at any given point there is a tangent line, and that tangent line has a slope, and that is what derivative is. Now notice that if a function is increasing, whether this way or this way, if the function is increasing, then notice that the slope of the tangent line is actually the slope of the tangent line is positive, as you see here, right? See, the slopes of all of these tangents are positive, and the slope of this tangent line is positive, this tangent line is positive, right? So as you see, as the function is increasing, the slope of the tangent line remains positive, right? So and it's also true that if a function is decreasing, either this way or this way, then notice that the slopes of these tangent lines are all what? All negative. That means from left to right. If you go from left to right, they fall. Here, from left to right, they rise, right? And the same is true if the function is decreasing this way, right? And later we're going to talk about this idea that what is the difference between increasing this way and increasing this way? How can we tell? And we're going to talk about that. But for now, we know that if a function is increasing, then the derivative is positive, and if the function is decreasing, then derivative is negative. So here is an example. You see here the function is increasing, so derivative is positive. On the top here, derivative is not defined. And then derivative is negative all the way to this point. At this point, derivative is 0. And then derivative is positive, and then all the way to this point, derivative is 0. And then it's positive again, 0 again. And then it's negative, right? So that means if we figure out the sign of derivative, then we can figure out how the function behaves, whether it's increasing or decreasing. So now, of course, these points are critical points where the function has a derivative that is 0 or undefined, right? Those are called the critical points. So here we have, this is a critical point, 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 right? All right. Now notice that at a critical point, we have a local max if the function is increasing to the left and then decreasing to the right. So if the derivative of the function goes from positive to negative, that indicates that there is a max at that point. Now, so if the derivative, what about if the derivative is 0? Well, derivative is 0 here. To the left of it, looks like derivative is negative, and to the right of it is positive, right? So what does that mean? That means this is a min, local min. Now over here, notice that derivative is, before this point, derivative is positive, and it remains positive to the other side as well. So if the derivative doesn't change sign, that means this critical point here is not an extremum, right? So the derivative, the first derivative has to change sign. Now over here, the derivative to the left of this point is positive, and to the right is negative, right? And that point is a local max. All right. So those are called the local extrema, of course, you know that, right? Now this one is not a local extremum, as I said, because the derivative doesn't change sign. All right, and that is, you can stop the video and read this yourself, but basically what it says is that if f prime changes sign from positive, I just described it, right? When we have a point, let's say at C, and f prime at C either 0 or f prime at C is not defined, does not exist, then if f prime changes sign from positive to negative, obviously you know the function is doing up this way and down this way, so that's a local max. And if we have such a situation but f prime changes sign from negative to positive, that means the function is decreasing and then is increasing. So at this point we have a min, right? So that's the idea described here, and you can stop the video and read it. All right, so it says use the first derivative test to find the locations of all extrema for this function. Use a graphing utility to confirm your results. Okay, so the first thing we have to do is think of the domain of this function, which is all real numbers, right? It's a polynomial. Then we're going to take the derivative. So derivative is 3x squared minus 6x minus 9, right? And then we're going to find what makes the derivative 0. And this is just algebra. So there is negative 1 and 3, right? Now at negative 1, the function, we can put this in the calculator in y1, right? We have seen this before. You put the function in y1, go to table set, and make sure table set is set to be ask instead of auto, and then go to table and put in negative 1 and 2, right? We have done this before in the other chapter. But the reason we do that is because we want to know the y coordinates of these 2 points, right? Later we're going to use them to graph it. But for now, we have negative 1 and 3, so we have 2 points. So what we're going to do is we're going to create a table. The first row of the table would be the domain of the function, which is the x values, right? And the x values here go from negative infinity to infinity, negative infinity to infinity. Now in the middle of this row, we are going to put interesting numbers that we found. In this case, we only use the critical numbers. Later, we're going to add some more important numbers here, but for now, only the critical numbers, negative 1, 3, in order, right, from the smallest to largest. Now, the second row of the table, we're going to put f prime, and the third row is the function itself. And then we're going to go to row, second row, and you can put lines here, or you can put kind of columns like this, right, at these points. And we know that f prime is 0 at this point and is 0 at this point, right? Now these 2 points divide the domain into 1, 2, 3 regions. So we can take test points from each region. Let's say from here we could take negative 2 and put it in the derivative and see what the sign of the derivative is. So if I put a negative 2, this is a negative 2. If I put a negative 2 here, that would be negative. This would be negative. Negative times a negative is positive. So the derivative is positive here to the left of negative 1. Then we pick a number between negative 1 and 3, maybe 0, right? And then we put it here. If I put a 0 here, that would be negative. If I put a 0 here, that would be positive. Positive times negative is negative. So between -1 and 3, the derivative is negative. And then we pick a number after 3, maybe 4. Put it in the derivative again. 4 minus 3 is positive. And 4 plus 1 is positive. Positive times positive is positive. So derivative is positive here. Okay? So we know that over here, the function, which is the third row, is actually increasing. Over here, the function is decreasing. And over here, the function again is increasing. It means that we have what? We have a relative max at -1, and we have a relative or local min at what? At 3. Why? Because we know the function is decreasing and then is increasing. So there is a local min here. Over here at -1, the function is increasing on the left and then decreasing on the right. So this point is a local max. So that's the idea, and later we can actually use all of these to graph the function, but for now I'm just going to show you the graph of it. As you see, this is increasing, right, to the left of -1. That's about -1 right there, right? The scaling is a little different on y and x-axis. So that's a -1. At -1, notice that the function value is 4 right there. You see, that's kind of 4 right there. So that's that point, which is the local max. And this point is right here. And I extended the graph so the points would match the table, right? As you see, the function is increasing to this point, then decreasing to this point, then increasing to infinity. Now something else is going on here, and that is over here. Notice that as the function is decreasing this way, and then about maybe right here is decreasing the other way, right? Is this way. So it's like it's decreasing this way and then that way. So we call this concave down, and this is concave up. And we're going to talk about that in this section later, how we can determine whether a function is concave up or down. But for now, we can easily find the critical numbers, put them in the domain here, right? And then figure out the signs of f prime in the entire domain. And based on that, determine where the function is increasing, decreasing, right? All of that. And here we just had to find the locations of all local extrema, and we did. These are the locations. So there is a local max at -1, but what is the local max? Is 4. And there is a local min at 3, but what is the local min? -28. So that number right here on the y-axis is -28. Okay. Find intervals in which function is increasing or decreasing. Okay? So how do we do that? Well, we're going to do sign analysis for f prime. So we're going to find f prime, which is basically 4x to the third minus 12x to the second plus 8x. And set it equal to 0. This is just algebra. Factor it. We've got 3 numbers, 0, 1, 2. All 3 are critical numbers. Why? Because they make f prime 0, right? Now, is there any x value that makes f not to have a f prime? That means not to have derivative? No, because derivative is a polynomial and is defined everywhere. So there is no points that make it undefined. So these are the only critical numbers. So we use the same trick. We create a table. First row, I'm going to put what? The domain is Aryan numbers. Put all the critical numbers here. They divide the region into 1, 2, 3, 4, right? And then we're going to do the check on the sign of derivative, right? And to get the sign of the derivative, you could just use looks like I have 2 calculators. Okay, so you can just put the derivative in the calculator. Let's see, what's the derivative? Derivative is 4x to the third power, 4x to the third power minus 12x to the second power plus 8x. So what you can do is you can go to table set here, make sure the independent variable is on ask, and then go to second table right here, second table, there we go, and then just put those numbers in there. We want to know what is the sign of f prime in this region here. So pick a number, let's say -1, and we'll put it in the calculator and see what the sign is. The sign is negative, so we put negative there. And a number between 0 and 1, well, let's say 0.5. And the sign looks like it's positive, right? So this is positive here. And then after 1, we put 1.5 maybe. And the sign is negative. So here the sign is, again, negative, positive, and negative. And then we need one more, and that's after 2. Let's put 3. Right? And it's positive. So that's how we can do sign analysis for f prime. Now we know the function is decreasing here, it's increasing here, decreasing here, and increasing here. So we have a local min at 0, we have a local max at 1, we have a local min at 2. In what interval is this function increasing? Well, we can say this function is increasing, right? We can say this function is decreasing in the interval from -infinity to 0. Now, if function is continuous at 0, you can include it here, right? And also, when you do the interval that is increasing up to this point, that would be from 0, right? You can include it here too, that's okay. To what? To 1, right? And you can include 1, 2 as well. I'll get the eraser here. And the pen back. So you can include the 1, 2, from 0 to 1 is increasing, right? And then from 1 to 2 is decreasing. You can again include 1 and 2 because they're part of the function, right? And then from 2, right, again, from 2 to infinity is what is increasing. So increasing here, decreasing here, increasing here, decreasing here, right? Those are the intervals, okay? All right. It doesn't matter, you include the 0 here twice, that's okay. Because it is decreasing from -infinity to 0. Because if you go to the left of 0 to any point, right? You go to any point to the left of 0, right? The function is decreasing to the left of 0. And also if you go to any point to the right of 0, right? The function is increasing to the right of 0, right? So 0 is included in this interval. All right. So, and that is the graph of it, of course. Use the first derivative test to find the location of all local extrema for this. Use a graphing utility to confirm your results. Okay, well, this, again, we have to get the derivative, right? Derivative of this is a little bit more involved. It's nothing really difficult. It's just a little bit more algebra. So negative 1/3 goes in the front. So 5 times 1/3 is 5/3. X to 1/3 minus 1 is -2/3. Minus 5/3 times x to 5/3 minus 1. 1 is 3/3. So 5/3 minus 3/3 is 2/3. Okay, now we can take the 5/3 out. And we can write this as 1/x to 2/3, right? Bring it to the denominator. And we can give both of these denominator of x to 2/3. So we leave this alone. If you multiply this numerator and denominator by x to 2/3, what do you get? Well, if you multiply x to 2/3 times x to 2/3, what do you get? Well, you get x to, what's 2/3 plus 2/3? That's 4/3, right? Over x to 2/3. So that is the same as this right here. So when you subtract, the denominators are the same. So 1 minus x to 4/3 is in the numerator. Now, obviously, this is f prime, so there is a number that makes the denominator 0. That means it makes the f prime undefined, and that would be x equals to 0. So that's one critical number. And then we set the numerator equal to 0. See what we get? Well, 1 minus x to 4/3 equal to 0, so x to 4/3 equals to 1. So what do? We take both sides and raise both sides to 3/4. Again, raising to 3/4 is like taking 4th root, so you have to put plus and minus, right? So on the right, this would be, when you take 3/4, you see, when you want to take this 1 out of here, right? When you want to take this 1 out of here, you only get 1. But the plus and minus comes from the fact that is actually from the left side. When you take the x out of here, you have to put plus and minus, right? So that's why. That's why I didn't put it here, but I put it here because when I get the x out, I get it, right? So really what we have is, let me explain it actually well here. So what we have is, out of here we get plus and minus x equals to 1, which is the same as x equals to plus and minus 1. Okay, so we got 3 numbers, right? And it says, use the first to find the locations of all local extrema. So right now what we have is the critical numbers. We don't know if we have extrema here. We have to do what? We have to do sign analysis for what? For f prime. So let's do that. So let's do sign analysis, okay? So here's the sign analysis. So we got negative infinity to infinity, and the numbers we found were negative 1, 0, and 1. Now, to put this in the calculator, you can either use fractional powers, or you can do this. I think it's easier with the calculator. We use fractional powers, but that's what they mean, right? So we're going to put this in the calculator. Don't forget to put parentheses here, and we could put parentheses here just to be sure. And then you do the same trick. You go to what? You go to the table and put these numbers. Let's say we pick a negative 2 here. If I put negative 2 in the derivative, what do I get? I get a negative number, so that's negative, right? And between 0 and negative 1, we can put negative 0.5. Negative 0.5, I get positive. So that would be a positive. And between 0 and 1, I can put 0.5, and it's positive. And then after 1, we can put 2, and you see it's negative. That's negative. So this function does this. Down, goes down to this point, and then goes up. Then goes still up this way, and then goes down, right? So we know at this point, we have what? We have a local min. At this point, we don't have local min or local max, right? Because the derivative doesn't change sign, right? And at this point, we have a local max, right? So that is how we figure out what's going on. What's going on over here is that derivative does not exist, so that means the tangent line looks like becomes vertical. So there is a vertical tangent at 0. There is more going on around here, because you see this is decreasing at some point, right? And is increasing to this point, right? So it's always actually increasing and decreasing concave up, and here always is concave down. All of that we can figure out later, but for now, just the extrema, the local extrema, and the location of them, and how do we know whether we have a local extrema, and how do we know whether we have a local min or local max, or none. All right, so concavity and points of inflection. Now notice that when a function is decreasing this way, as you see, right? So here are the slopes of the tangents, right? Let's estimate what that slope is. Let's say it's -4, the slope of this. And the slope of this, what would that be? It would be closer to 0. It would be less steep, right? So it would be, let's say, -3. And then this here would be like maybe -2, -1, and so forth. It looks like we are going from -4 to 0 at this point. So that means the slopes themselves are increasing, right? So here's f prime. Remember, slopes are f primes. So f prime values are actually increasing. If f prime values are increasing, then the derivative of f prime has to be positive, right? According to what we just learned about derivative, right? So in the previous examples, we know if a function is increasing, then its derivative is what? Is positive. But here the function is actually f prime itself is the function. So if f prime is increasing, then its derivative, which is f double prime, has to be positive, right? So we say that whenever we have a shape that we call it concave up, is think of cup up, cup down, something like that. So if it's concave up at any given point here, it means at those points f double prime has to be positive. Now what about if the function is increasing this way? The same thing happens. Notice that we start from 0, and then these slopes are actually, looks like they're getting bigger, like 0.5, maybe 1, maybe 2, maybe 3, and so forth, right? So it looks like from here to about here, at this point, right, the function, the f prime values are actually still increasing, right? So that means f double prime has to be positive. So even over here, f double prime has to be positive. Why? Because the slopes of the tangent lines are increasing up to this point. Now what's going on over here? Well, the function is increasing. That means f prime is still positive, but let's say f prime starts from, let's say, 3, and then what number does it approach? 0. So it goes from 3 to 0. That means f prime values are actually decreasing here. So f prime values are actually decreasing. If f prime values are decreasing, then f double prime has to be negative, right? So over here, when the function is concave down, f double prime is actually negative. Now what about over here? Well, the function is decreasing. So what is going on with the slopes? Slopes start from 0, and they go to what? They go to negative numbers. Let's say this is like -0.5, -1, maybe -2, -3, and so forth, right? So we start from 0 and we go to negative numbers. What does that mean? That means, again, f prime is decreasing. So f double prime has to be negative. So over here as well, f double prime has to be negative. All right? So that is called concavity. The shape of the graph is called concavity. So how do we know whether the function is concave up or down at any given point? All we have to do is find f double prime and do sign analysis for f double prime, right? Now notice over here at this point, right here, at this point, the concavity of the function changes, goes from up to down, right? And if that happens, f double prime changes sign, right? Now notice f double prime here is positive, and right after this point, it becomes negative. So when f double prime changes sign, we have points that are called points of inflection points. So at an inflection point, the function double derivative changes sign, right? So that's the idea. Another idea you should notice here is that whenever we have f prime 0 at a point, there are two ways to figure out whether this is a min or is it a min or is it a max. The way we can figure it out is this. We say, okay, is f double prime positive or negative over here, right? And as we discussed, since this is concave down, right, then f double prime is what? Is negative, right? So if f double prime is negative, that means the function is concave down at that point. And if it's concave down, that means that point is a max, right? Now over here, we know the function is concave up here. That means f double prime is what? Is positive. And if f double prime is positive, what does that mean at this point? It means that the function kind of looks like that at that point. So this has to be a min, right? And that's called the double derivative test or second derivative test. So that's the second way to figure out whether we have a min, local min or local max, right? At a critical point. Now, this test doesn't work if f double prime equals to 0 at that point. So this test fails. We have to go back to what? Looking at the sign of f prime to figure out whether this is a min or max. So if f double prime is 0, this test actually fails. Okay? All right, so let's look at some examples. It says for this, find all intervals where f is concave up and intervals where f is concave down. Find all inflection points. So to do this, we need to find f prime and we have to find f double prime. But notice that we are not told to find critical numbers or do anything else. We just have to find the critical, we just have to find the inflection points. And to find the inflection points, we have to see where is it that f double prime is 0, okay? So you can think of this as the critical numbers for f prime as a function, right? So when is f double prime 0? And where is f double prime, right? Where is f double prime? Where is it? Does not exist. And where f double prime is 0. These are actually the potential what? Inflection points, right? And you can think of the points that you find here as the critical numbers of f prime, right? Okay, so let's do that. So we take f double prime, take f prime first, and then we take f double prime, we get this. Set it equal to 0. Well, we get what? We get x equals to 0.5. So there is only one point, right, that we have to worry about. So we can do a table, but this time we don't care about f prime because we are not told to do anything about that. So we don't want to do something we're not told to do. So this is the domain of the function. This time we put the only interesting number Well, the only number we're interested in, which is 0.5 here, and then we make a row of f double prime and then one for f. So we know f double prime is 0 at this point. To the left of it, we can pick a number, let's say 0. I'll put it in here. Well, looks like we get a positive number. So to the left of 0.5, f double prime is positive. To the right of 0.5, let's say 1. Put a 1 here. That would be negative. So what does that mean? Well, it means that f double prime changes sign at what? At 0.5. So that means f double prime is actually concave up, right, over here, and it's concave down over here, right? Now, I don't want to graph it because we didn't care about whether it's increasing or decreasing. We just figured out that f double prime actually is positive. That means whatever f prime is increasing, and over here, whatever f prime is decreasing, right? So the function might be looking concave up, maybe it's decreasing this way, right? Or maybe is increasing this way, we don't know. But we know it's concave up. Same is over here. Whether it's decreasing this way or maybe it's, so it's concave down, right? Or it can actually increase concave down, right? We don't know. And we're not asked to figure that out. Okay, so that's how we find inflection points. And that's the graph of this function. And notice that is part of this interval, the function is decreasing and then is increasing, right? So notice that over here is all concave up, whether it's decreasing or increasing. But at this point, what happens, the function changes concavity, right? Concave up, concave down. All right. So second derivative test, I explained that already. I said that if f prime is 0 or f prime is, if f prime is 0, we have a critical number, and f double prime is negative, that means that number is actually a local max, right? If f prime at the point is 0, and then f double prime is positive, then f has a local min, right? And we see here point A, point B, right? And if f prime at c is 0, but f double prime also is 0, then the test is inconclusive. That means this test doesn't help us. I have an example over here. When f prime is 0, and also f double prime is 0, right? So what do we have at this point, whether it's min or max? This test doesn't tell us. What do we have to do? We have to do sign analysis for sign analysis for f prime. So we know f prime here is negative, and f prime here would be positive. So f is decreasing here, and f is increasing here. So we know that's a local min. But we wouldn't be able to tell that from the second derivative test, right? All right. Find all local extrema using second derivative test. Okay, so let's do that. So first we take f prime, and then f double prime. So we set f prime equal to 0, right? And we're going to end up with these two numbers. So these are our critical numbers, right? And then we're going to take f double prime at -2 and see whether it's positive or negative. And looks like is what? What is f double prime at -2? It's positive, right? If we put a -2 here, that would be a 12 plus 3, 15 is positive. So we have a local min at -2, and at 3 is negative, f double prime is negative. So we have a local max, right? And the picture of this looks like this, right? So that's a local min, and that's a local max. Again, in the next section, we're going to use all of this information, all the tools we're developing, to actually graph a function. get all the points under control, the behavior at different intervals, right? But for now, we're just increasing number of tools that we can use to do that. And notice that graphing in algebra and pre-calculus was much, much harder than graphing in calculus, because in calculus we have a whole lot more tools to use. All right, so analyze the graph of f prime and then list all intervals where f is increasing and decreasing and where minima and maxima are located. Now, one common mistake here is that you think that this is the graph of f, but it's not. We are told it's the graph of what? F prime. So this is the graph of f prime, is not f. Okay? All right? So if you look at the graph, you see that over here, f prime is positive. Right, to the left of -2, f prime is positive here, right? F prime is positive. Over here, this whole region right here, f prime is negative, right? Because it's below x-axis, is negative. Over here again, the whole region way over here, all of this, f prime is greater than or equal to 0, right? It's either positive or is 0 at this point, but it's again, it remains positive. Positive here, right? All right, and over here, this whole region, f prime is actually negative, right? And after here, again, f prime becomes positive. So right now, can we tell where the function is decreasing or increasing? Yes, over here, the function is increasing. Now again, don't confuse this with the function. This is decreasing, but this is what? This is f prime, not f. So over here, the function is increasing. Over here, the function is decreasing. Over here, the function is increasing. Over here, the function is decreasing. And over in this interval, the function is increasing. Right? And you can tell the interval from 1 to 2, 2 to infinity, right? -1 to 1. Again, in this interval, the function is increasing. So it would be from -1, you can include -1, to 0, you can include 0. And then union from 0 to what? To 1. But then why don't we just put from -1 to 1, right? The function is increasing. And so forth. So let me show you the answer for this, right? All right. Now, now what about where the minima and maxima are located? Is there a min or max at -2? Yes, because f prime changes from positive to negative. What does that mean at -2? It means the function is increasing and then is decreasing after this point. So there is a max at that point, right? And what's going on here? Is there an extrema there? Yes, because the f prime goes from negative to positive, right? That means the function is decreasing and then is increasing. So there is a min there, right? What about here? Well, there is no min or max at that point. Why? Because f prime remains positive on both sides. What's going on here, we don't know, but we know it's not a extremum, right? What about here? Well, f prime goes from positive to negative, so it goes up and then down. So it's a local max. What about here? Well, f prime goes from negative to positive. So the function is decreasing and then increasing. So there is a min there, right? That's how we can tell where the points are. And I just described it. So you can stop the video and read all of these and make sure they make sense to you, right? All right, so I'm going to move on and we're going to do we're going to graph this, right? Now, if you graph this with the calculator, you're going to see that you're not going to get the correct graph unless you actually do some zooming. So let's not use calculator and use calculus. So how do we graph it? We take f prime and f double prime. Those are two of our tools, right? F prime, set it equal to 0, we find critical numbers. F double prime, we set it equal to 0, we find inflection points, right, if there are any. So let's do that. So here's the table. The domain is all real numbers. We found 3 numbers, plus and minus 20, make the f prime 0, and 0 makes f double prime 0, right? So we put them all 3 over here. Now, f prime row, f double prime row, and f row. Now we can do some sign analysis. From negative 20 over here, we can pick a number, let's say negative 21. If we put it in f prime, obviously negative 21 squared is bigger than 400, so f prime would be positive here. And if you put a number from 0 to negative 20, let's say, negative 10, with negative 10 here, that number would be smaller than 400, so it would be a negative, right? And it is true for all of these numbers, all the way to the other root of f prime. So you see f prime is 0 here, and f prime is 0 here. So it divides the region into 3 parts, 1, 2, 3, right? So f prime is negative here, and after 20, obviously, if you put a 21 here, this number is greater than 400, so this is positive, right? Now, f double prime is 0 when x is 0, right here. That divides the region into only 2 parts, this part and this part. But we're still going to take these divisions into account because we want to know what's going on. We want to relate f double prime with f prime. So that's why I still have this division here, right? So we have only one region to the left of 0, and this whole thing is one region. So we just need one number to the left of 0, any negative number, and substitute it in here, we get negative. So this is all negative. And anything to the right of 0 makes this positive, so this is all positive, right? So positive, positive, and negative. All right, so let me get rid of my lines because already there, right? So what's going on over here? Well, over here in this interval, to the left of negative 20, the function is increasing and it's concave down. So it's going to look like this, increasing, concave down. And what's going on between 0 and negative 2? The function is decreasing because f prime is negative and it's concave down. So it's going to look like this, right? What's going on over here? The function is still decreasing, but it's concave up. Decreasing, concave up looks like that. And over here is increasing, concave up. Increasing, concave up, right? So that's how we get the behavior of the function. These are just points, right? We can substitute negative 20 in here and see what we get. We can substitute 0 in here, of course it would be 0. And we put 20 in here and see what we get. And then we graph those points and we can graph this function, right? So we got all of that. Make sure you stop the video and read all of that, see it makes sense to you. Now here's the graph. You see, before negative 20, if you put it over here, we get, what do we get? We get some number, some big number, 500 something. So that's right here is this point, right? Negative 20 and its y coordinate, right? And this point right here is actually this one. And this point right here is 0, but you put 0 here, you get 0, 0, 0, right? So to the left, notice that it's increasing, concave down, between negative 20 and 0 is decreasing concave down. From 0 to 20 is decreasing concave up. And from 20 on is increasing concave up, right? And later we're going to talk about the end behavior. So you know the function goes to infinity this way and you go to negative infinity this way. But for now, we want to get the connection between f prime and f double prime and what they can do for us in graphing functions, right? We don't want to learn all the tools at the same time. It gets confusing. All right, so make sure you get everything I just said before you move on. And so using a calculator, look what happens when we put in the calculator. We get this. Even in a computer, we have to zoom out a whole lot in order to get the correct graph. You see what we get with the calculator? You go to zoom standard. That's what you get. You get like a straight line, which is not that graph, right? But you have to zoom in, right? I said zoom out, zooming out many, many, many times, right? In order to get the shape of this, right? So so that's what we get. Let me now that we're at it, before we finish this, let's actually go to let's go to GeoGebra. Let's see. Go to GeoGebra and graph this function. We can also go to calculator and graph this function, and then we use GeoGebra as well. So let me close this. Let me put it in the calculator first, and I have to turn off my other graphs. There you go. And then I'll put 1/3. Let me clear that. And put 1/3 of x to the third power minus 400 x. And I want to go to zoom, let's say zoom 6. And I can get anything, right? 1/3 of x to the third minus 400x. What about zoom, let's say zoom fit. There you go, zoom fit. Zoom fit gives me what? Gives me this, right? So I'm going to go trace, right? And then let's say, let's go to zoom in and see what we get. Press enter. Now what do you get if you zoom in? Well, you're going to get what? You're going to get the same thing, right? You get even smaller, right? So let's see. Let's go to, so let me go to my GeoGebra now, and then do the same thing. I'm going to put x to the third minus 400, and put y equals to, let's see, 1/3, right? Y equals to, my keyboard is not in English, so x to the third power, and then minus what? 400x, right? So notice what I got here, and that's what we couldn't see in the calculator. So you see, we got something that if I zoom out, I can actually see it. See? Let me move this way. I'm going to have to do a lot of zooming out to see it, because the values are so big, they're outside of the calculator windows, right? Or the computer windows. Notice the values are like thousands. So that's why you couldn't see it, right? All we saw was like a vertical line, and that's what calculator zoom fit brings it in, but it doesn't still show you exactly what's going on, right? So you had to zoom out to see it, because it was like graph was over here and over here. We couldn't see anything at first, and zoom fit brought it to a window, but it still doesn't give you a good shape. Okay, so here's an example that shows calculus is better than calculator, maybe. All right, so I'm gonna call it a video here and go back and say bye to you, and I see you. Take care of yourself and others, and I see you in the next video. Okay.